Hi, my name is Miranda Williams, and this is Lab 3 over black holes and orbits. So the purpose of the first part of the lab was to code for the calculation of the unknown mass of the black hole that is being orbited around by a star of known mass. The second part of the lab was to find the trajectory of the path between objects that are interacting with each other, which is a spaceship, a planet with a moon that is orbiting around a star. The models that were used to find the unknown mass of the black hole was Newton's second law, curving motion, both parallel and perpendicular components, the velocity update, and position update. The models that were used to find the orbital path between the star, the spaceship, the planet, and the moon was the gravitational force, Newton's second law, and the position update. So these are the main physics ideas presented here. We use second law so that we could update the momentum. And so we use that so we could find the change in the parallel and perpendicular forces. So we could go ahead and graph them with the computational model. And we use the curving motion for both for the first part of coding. So we could draw the arrows to represent the curving motion of the objects, the net force, the parallel force, and the perpendicular force. We use the position update formula with the second and first computational model so that we could be able to accurately have the paths that are being updated with the interactions that are happening. The velocity update formula was used as well, and the gravitational force was mainly used for the second computational model because we're calculating the trajectorial path between the objects. So for that, we need to find the gravitational force of each object acting on the other one. So this is again just stating what we said before, the system of the first computational model is the orbiting star and the surroundings of the black hole in the space. And then the system of the second computational model is the spaceship and the moon, and the surroundings are the planet and the star. So here are the initial conditions for our first computational model. So we have G, which is the gravitational constant that we needed. We also have the mass of the star, and we also have delta T, which is the amount of time that we were calculating for, and that is in seconds. Next, we have the initial conditions for the second computational model. So we needed to know the mass of the planet, the moon, the ship, delta T. We need the gravitational constant so that we can go ahead and do the force of gravitational equation. And we have all the other initial conditions for the moon and the spaceship. So here is the first computational model. So we had to find the net force of the parallel and perpendicular forces, and the calculation of the perpendicular and parallel forces will later be used to generate arrows that will follow the parallel and perpendicular motion of the star's orbit around the black hole. So we had to calculate the parallel and the perpendicular components. With the parallel, we had to find p hat. We also had to find the magnitude of momentum, sorry. And we also had to find put it all together and find dp dt parallel. And then with that, we plug that into the fnet parallel. Next, we have fnet perpendicular, and we know that fnet is equal to fnet parallel plus fnet perpendicular. So all we had to do to find dp dt perpendicular was do fnet minus fnet parallel. So our first computational model, you can see the different arrows that were generated by doing the calculations of the parallel, perpendicular, and fnet force components. So the orange arrow represents the net force between the star and the black hole. The small magenta arrow right here, it's a little bit hard to see. It represents the parallel force of the star's orbit, and the cyan arrow represents the perpendicular force of the star's orbit. And then we also had to put in a computational model so that we can calculate the mass of the black hole, and that is this right here. And we found that the mass of the black hole was 2.09 e to the 34 kilograms. Next, we have our second computational model, and all these lines of code are mainly coding for the gravitational force on the different objects. So we have the different ones of the planet on the moon, we have the ones of the ship on the moon, we have the ones of the planet on the ship, and we have the moon on the ship, just so we can get an idea of the trajectory path between all of the objects. And so this is what that looks like whenever it's all computed, the code for the gravitational force between the objects allows for the trajectory path to be outlined and display the relationship between the objects. The cyan path represents the moon's path, and then the magenta path represents the spaceship's path. So our conclusion: sources of error, that could be setting up the wrong variables for specific equations or using the wrong equations for indicated values are being asked for. Additional questions: so the net force and its parallel and perpendicular components are different from the rate of change of its parallel and perpendicular components, because the parallel and perpendicular components in net force changes the speed and direction, while the parallel and perpendicular components for the rate of change changes the magnitude and direction of momentum. If I want to predict the motion of the system of a black hole, a star, planet, and moon, I would need to calculate the force of gravitation between all of the
let's crank
objects.
this out.